All right, 6.3, which is sampling distributions and estimators. So 6.3, sampling distributions, and estimators. So one of the questions was the very first question. So question 1, it asks this. It says there are about 11,000 births each day in the United States, and the proportion of boys born in the United States is 0.512 or 51.2% are boys. Assume that each day 100 births are randomly selected, and the proportion of boys is recorded. So A, what do you know about the mean of the sample proportions? And then B, it says, what do you know about the shape of the distribution of the sample proportions? So really this section is kind of leading us into what's 6.4, which allows us to take proportions or probabilities, of sample means. So what we want to know is we want to talk about the mean of the sample means and how that relates to the mean of the population. And it's an estimator, and I want to know eventually, is it biased or unbiased? So what we'll know is that the mean of the sample means, nice word, sample means, is equal to the mean of the population. So what does that actually mean, for lack of a better word? So say that we take a bunch of samples of size 100. And what we know is that, remember, this is not real data. This is kind of what's going to happen if you did this. So I know that the mean is 0.512. But I know if I take like a sample of 100 children, say at the hospital nearby, I'm going to get an X bar. So I'm going to get a sample mean, and that sample mean is probably not going to be exactly 0.512. It probably is going to be close, right? So we know the idea of this is these X bars should be pretty close to the actual mean of the population, but every sample is going to have a little variation. It's going to have a little wiggle around that. What you're going to get is you're going to get a lot of means that are really close to that actual number, that 0.512, but you're going to get a couple that are a little high and a couple that are a little lower. The higher you go above, the less you're going to get. So essentially you might get something like this, like 0.523, and the X bar is equal to 0.5051, and so on. What you're going to see is you're going to see numbers bounce around that actually mu of 0.512. So you're going to see a little couple above, couple below. Heck, you might even hit it every now and then. So what that actually looks like kind of is, well, let's answer A then. So what it's asking is, what do you know about these sample means? Well, I know that they're going to be very, very close to this mean right here. There's going to be a little wiggle. But the idea is if you add up all these sample means and divide by how many you get, theoretically, you're actually going to get exactly this number. So it means this means of all these sample means. So if I take, like this is X bar 1, X bar 2, X bar 3, and so on. So if I take the mean of those sample means, so X bar 1 plus X bar 2 plus X bar 3 plus forever all the way up to X bar sub n, and I divide by how many there are, which there'll be n of them, what you're going to get is you're actually going to get 0.512. So the mean of the sample means, the mean of these sample means is equal to the mean of the population. So for part A, what they asked again is, what do you know about the mean of the sample means? Well, you know that it's going to be equal to the mean of the sample, I apologize, the sample proportions. I apologize. These are proportions, not means, but it works for means as well. So this is not really X bar, these are little p's. That's my bad. These are little p hats. P hats. So 1, 2, 3. So P1, P2, P3, Pn. What you know is it's going to be equal to the population proportion, so this will actually be equal to P. So that's a little bit better. What's interesting is the reason why I kind of confused it with the mean is because both of these things are considered unbiased estimators. And what's meant by an unbiased estimator is if you take the mean of these sample proportions, it's going to be equal to the population proportion, that the mean of the sample statistic is actually equal to the population statistic. And that's what it means to be an unbiased estimator. And I'll show a couple examples of biased and unbiased estimators. Basically, another way we could actually say that is that these values target this value, is another way of saying that. So B, it says, what about the distribution of the population proportions? Well, the distribution is going to be very similar. P, which is going to be equal to 0.512. You're going to get a lot of them that are very close to this mean. Some of them are going to be a little bit below. Some are going to be a little bit below, and some are going to be a little above. And what you'll notice is you get this nice bell-shaped curve. That the distribution of the sampler proportion actually has a normal distribution, and that's part B. So it's going to be a normal distribution. All right, so let's do some examples outside of the book, because the book actually uses 3 particular numbers and asks you to do all these things. So I'm just going to randomly generate 3 numbers, and then we're gonna determine what ones are biased and what ones are unbiased estimators. So what I'm going to do is I'm going to pick a population of 3 numbers. So I don't know, let's say 3, 7, and 12. There. Those are 3 numbers. This actually works with any 3 numbers. That's why I'm kind of randomly choosing them. So what the book asks us to do is asks us to take it has a population of 3, and it says take all samples of size 2 with replacement. So for the population, I'm going to have samples of size n equals 2. Now we're doing this with replacement. So the idea is this isn't a bag. I'm covering it up, and I'm grabbing random numbers out, and then I'm putting them back. The possibilities you could get is you could get a 3. Remember, you're putting the 3 back because it's with replacement, and you can get a 3 back. Or you could get a 3 and a 7. Or you can get a 3 and a 12. So that takes care of like the 3s and all the other numbers. Now you could get like a 7 and a 3, a 7 and a 7, and then a 7 and a 12. So that's all combinations with 7 in front. And then with 12 in front, you 12 and 3, 12 and 7, 12 and 12. So those are all the possible combinations or possible samples of size 2 taken with replacement. So what I want to do is, in this case, I'm going to test to see if the mean is a biased or an unbiased estimator. So what we're going to do in this example, example 1, is I'm going to determine if the mean is a biased estimator or unbiased estimator. Okay, so in order to do this, what we're going to do is we're going to I'm going to take all these samples. I'm going to find this statistic. In this case, is going to be the mean. So these are going to be all our sample means. So over here is going to be our sample statistic, whatever statistic we're choosing to do. Example 1 or problem 1, they are saying let's use a statistic of proportion. Well, in this case, we're going to use a statistic of mean. So in order to find the mean, I'm just going to take the mean of these lines individually. So the mean of 3 and 3 is 3 plus 3 divided by 2, which is equal to 3. So the mean of this is 3 plus 7 divided by 2, which is equal to 5. This is going to be 15 halves. So 7.5. This one's going to be equal to, what's nice is if you know 3 and 7, 7 and 3 are going to have the exact same mean, so this is going to be equal to 5. The mean of 7 and 7 is going to be 7. This is going to be 19 divided by 2. This is 9.5. So really when you calculate these things, like, certain statistics are easier than others. Like these ones are not too bad. But eventually I'm going to do like stuff like standard deviation and other things. So, 7.5, which we've already calculated. If you know this one, you know this one. 7 and 12, which is going to be the same as this, which is going to be 9.5, and then 12 and 12 is going to be equal to 12. All right. Now when we're done with that, what I want to do is I want to actually they put something over here as far as probabilities. We'll get to that in just a minute. So what I want to do is I want to determine if this is a biased or unbiased estimator. So what I need to do is I need to take the mean of these numbers. So you're always going to be taking the mean of this column here. the mean of whatever sample thing that we're doing. So the mean of the sample means is going to be equal to, so what I'm going to do is I'm going to add them all up. 3 plus 5 plus 7.5 plus 5 plus 7 plus 9.5 plus 7.5 plus 9.5 plus 12 and divide by 9. So what I get here is I got it 7.33. So this was 7.3 repeating. So when I round it to one decimal past the given data, this is our data up here. So I'm going to say that the mean is going to be 7.3. I don't have units on here. I didn't specify. This could be like the ages of my children, for instance, but it's not. So, all right. Now, if I want to see if this thing is an unbiased estimator, what I have to do is I have to go back here and take the mean of the population and see what happens here. So this is, the mean of the sample means. So what about the mean of the population? Well, the mean of population is going to be equal to 3 plus 7 plus 12 divided by 3, and what we actually get is 7.3 repeating, so it's 7.3. So notice that what we say is that, sorry I didn't have there, but what we notice is that these two numbers are equal. Like the mean of the sample means is actually equal to the mean of the population. So this number targets this number. These sample means actually target this number. So since these numbers are the same, the mean, as far as standard, like as far as a statistic, is an unbiased estimator. Now, what you can also do is you can take this table and you can kind of shrink it by getting rid of the repeats, like 3 and 12 and 12 and 3 are basically kind of like the same idea. So instead of writing them as permutations, you can write them as combinations, and they say how many times they show up. Like this shows up once, this shows up twice. So 1 out of 9, 2 out of 9, 2 out of 9, and so on. So that's what they write over here in that other column. I'm more worried about what it targets. All right, let's do the same thing with standard deviation. Let's see if the standard deviation is biased or unbiased. So example 2. Let's test determine if the standard deviation is biased. It is biased or unbiased. Basically, I should say is a biased or unbiased estimator. Is what I should say, estimator. All right, so what we're going to do is I'm going to take the exact same population, might as well. So let's say our population is equal to those same three numbers. So I have 3, 7, and 12. And then what I'm going to do is I'm going to do samples of size 2. So samples n equals 2. And then now I'm going to do the sample standard deviation here. Okay. So when we set this up, it's the exact same column over here. You got 3 and 7. You have 3 and 3, 3 and 7, 3 and 12. You have 7 and 3, 7 and 7, and 7 and 12. And then you have 12 and 3, 12 and 7, and then 12 and 12. So those are the exact same columns that we had before. But now I have to find the standard deviation of these things. And standard deviation is not a very quick thing to calculate. And remember that this is also a sample. So what I'm going to do is I'm going to use my calculator to find these things. Now, it's easy to know the standard deviation of 3 and 3. Remember, the standard deviation is how much the number deviates from its mean. We know that the mean of 3 and 3 is 3. So that each of these values deviate 0 from its mean, which is itself. So this is going to be equal to 0. And we can kind of verify it as well. So to do that, you go to Statistics. I'm going to go to Edit, and I'm going to go. I'm going to put these numbers just into column 1. So I go 3, enter, 3, enter. And what I'm going to do is I'm going to find the standard deviation of that column. So stats, go to calculate, and then one variable statistics, and then I go down to here and calculate this thing. Oop, I have L4 there. That's not going to do anything. Quit. Try that again. Stats, calculate. I need to calculate L1, so second number 1, and let's calculate that. So just to make sure you guys know as a class, I'm not going to make you hand calculate the mean and standard deviation anymore. That ship has sailed, okay? I just wanted to do it on on exam 1, just so you know how to calculate it. Now that you know how to do it, let's just, let's use our technology to do everything. So you can see that this is the standard deviation of the sample, this is the standard deviation of the population, but these are samples, so I'm going to use the S of X. Now I need to do the other one, so stats, edit, and we're going to go 3 and 7. And then stats, go over to calculate, one variable stats, and then make that happen. So S is going to be 2 point, I'm going to take this out a little bit, 2.8284, that's good enough. And then we have 3 and 12, so stats, edit, 3 and 12, stats, calculate, enter. Okay. So this is going to be 6.364. Okay. Let's talk about some things that we can do quickly here. We already know that standard deviation of the number itself is going to be equal to 0, so those 12s are 0, so those can happen quickly. I know the standard deviation of 3 and 7 is going to be the same as the standard deviation of 7 and 3. They're both going to deviate the same amount from each other, so some of this stuff can be repeated. I did 3 and 12, so I can also do 12 and 3. So this is going to be 6.364. So I still have to do 7 and 12 and 12 and 7, so I just need to do one more. So stats, edit, 7 and 12, enter. So I'm going to go, so again, the way this is done, go a little slower. You go to stats, you go to this edit, hit enter, and you're going to line up L1 with whatever you need. Once you have that, you can hit stats again, press over to calculate, and then hit enter on one variable stats. Make sure that says L1 because that's where I have it populated. And this gives us standard deviation 3.536. 3.536. There's no real specific rounding method I'm doing here. I'm just trying to go out far enough. Like that's probably good enough. I'm just trying to go out far enough that I don't get any rounding errors. Technically, you should do this with the exact number, but I'm not going to. So, in order to determine if this is an unbiased estimator, what I have to do is I have to take the mean of this column. I have to take the mean of the sample statistic. In this case, this statistic is standard deviation. So the mean, always the mean, of the sample standard deviation in this case is going to be equal to, so I'm going to add up all the numbers, 0 plus 2.828 plus 6.364 plus 2.828 plus 0 plus 3.536 plus 64 plus 3.536 plus 0, just made it. And then divide by 9. So when I add these things up, we're going to see what happens. So what I get is I get 2.8284. You know, I'm definitely rounding error, so I'm just going to go to here. So if I'm going to do this technically, these are X values, so it's only going to go one decimal past the given beta data. So 2.8, I'm confident that that number is pretty spot on, 2.8. So now to see if it targets it, what I'm going to do is I'm going to find the population statistics. So in this case, the population standard deviation. And the way I'm going to do that is right on the calculator is go to stats, edit, and then I'm going to go 3, 7, 12, and I'm going to make it do it for me. So 3, 7, 12. Okay, so stats, calculate one variable statistics, and we get I get a standard deviation of 4.5. So this is 4.5. So, this is sigma. This is the mean of S of your sample standard deviations. So what we'll notice is that the mean of the sample means is not equal to the mean of the population. So it is a biased estimator. So therefore, we have a biased estimator. Biased because this number does not target this number. Now what's kind of interesting here is, we use mean and standard deviation all the time, so how can one be biased and one be unbiased? How is that useful to us? Like, how do we actually find population statistics? Well, the way we define population statistics technically is we take a bunch of we take a bunch of samples of a certain size, and we find the sample statistic for that particular, for each of those samples. And then we find the mean of all those samples. And what we know is the mean of that sample statistic should equal to the population statistic, assuming that it's an unbiased estimator. So we can get really, really accurate by taking more and more samples. But this won't work for standard deviation because it's an unbiased it's a biased estimator. But what's kind of interesting here is if I choose to not do standard deviation, but if I choose to use variance instead, well, the variance is just a standard deviation squared. So what I'm going to do is I can square all these numbers, and let's see if the variance is biased or unbiased. So I'm going to square all these numbers and see what happens. Well, I can do these ones, 0, 0, 0. I can square 0. The other numbers I'm going to need a calculator. So 2.828 squared. So I get 7.998, 6.364 squared, 40.5. That's good enough. This is 7.998, 3.536 squared, 12.503. Good enough. 40.5. 12.503. Okay. So if I decide to do this with the variance, I'm going to have to square all those numbers, right? So you'd have to square first, add second, just to make sure you guys understand that. So all these numbers are going to be different now, right? So in this case, this is going to be the mean of our variance, and this is going to, I could have left that. This could be our variance squared, so this is going to be squared. So when I'm done calculating these things, remember I'm adding these numbers up and dividing by 9, okay? So add them first, square them first, add them second, and then divide by 9. So taking the mean of those is going to be 7.998 plus 40.5 plus 7.998 plus 12.503, 40.5 plus 12.503. So what I get is I get 122.122,002. That's pretty good. And I wonder what 4.5 squared is. Oh, I messed up. Oh, I forgot to divide by 9. Divide by 9. Damn. What did I mess up? I have to check it. Give me 1 second. What a stinker. There's some kind of error here. Fortunately, I might have to redo this one, but I want to go back and check these numbers real fast. The standard deviation, actually, the variance actually is an unbiased estimator. These two numbers are supposed to be the same, so the fact I'm doing something wrong is my fault. So Oh, no. I got it. I know it's wrong. Never mind. We have to be careful here. Let me double check this number. I think I got it. So 22.002 divided by 9 is going to be equal to 13.56, 13.6. And we have to go back. I think I had that 4.5 wrong. So statistics, edit. So this was 3, 7, and 12. That's what happens when you do it live. So it's 3, 7, 12. And you go to statistics and you go to calculate. I think what I failed to do is, this should be the population, so I think I wrote the wrong number there. Yeah, I wrote 4.5, which would be the sample. It was supposed to be 3.6. But either way, you can see that 2.5 and 3.6 was not going to do. It does not target, so standard deviation is still biased. But if you take your 3.6 and you square it, 3.6 square, bam, you're going to get 12.96. Now remember, what I have is I have a lot of rounding errors here, but you'll notice that those numbers. So let's take it a little bit farther out. Let's take it out. So take it out even farther. So calculate. So it's 3.68. So it's actually 3.7. So this is 3.6817. Let's square that number instead and see if we get closer. So 3.6817 squared. And what I get is 13.55, which is my 13.6 that I had before. So we can see is that that it didn't work for standard deviation, but it did work for variance. That means that variance is an unbiased estimator. Now we can do the same method for all sorts of statistics. We can do it for proportion. We can do it for median. We can do it for range. I'll do one more. I'm going to do a proportion because I don't think it's super obvious. So if I want to do it for proportion, so is proportion a biased or unbiased estimator? Was it a biased or unbiased estimator? Probably should put some question marks. There you go. So I'm going to do the same population. I have 3, I have 7, I have 12. And then we're going to do, n equals 2 sample size here. So 3 and 3, 3 and 7, 3 and 12, 7 and 3, 7 and 7, 7, 7 and 12. And then 12 and 3 and 12 and 7, 12 and 12. So what I want to do is I want to determine, let's find the probability that the number is less than or equal to 7. So let's find the probability that x is less than or equal to 7. So in this case, what I'm asking is how many of these numbers are less than 7? So can you tell that both of those numbers are less than 7? So 2 out of the 2 numbers are less than 7. So it's a 100% chance that those numbers are less than 7, less than or equal to 7. Again, both these numbers are less than or equal to 7. So 2 out of 2 of those are less than or equal to 7. Only 1 out of 2 of those are less than or equal to 7. Both of those, again, are less than or equal to 7. Both of those are less than or equal to 7. Only one of those, 7, is the only one that's less than or equal to 7. 12 is bigger. One of those, 3 is the only one that's less than or equal to 7. Only one of those as well. And then 0 of those. So again, if you're determining if it's a biased or unbiased estimator, what I have to do is, again, I have to take the mean of our sample statistics. So what's the mean of the sample proportion? So I'm going to add them all up and divide by how many there are. So this is equal to 1 plus 1 plus 0.5 plus 1 plus 1 plus 0.5 plus 0.5 plus 0.5 plus 0. And then divide this by 9. What you'll see is I get 0.6 repeated. Now I know that I just rounded to 0.7 because it's 1 decimal past our given data, and our data is in integer values. It has no units because I didn't to find units on them. Let's find our population proportion. Population proportion. So this would be the mean of p hats. All these are little p hats, proportions of samples. And I know we've labeled them. Never mind, we'll get to it later. So then population proportion. The population proportion is going to be, out of these three numbers, how many of them are less than or equal to 7? Well, 2 of those numbers, 2 out of 3. So this would be equal to 2 out of 3, which ends up to being 0.6 repeating, which again rounds to that 0.7. And what we'll notice is they are exactly the same as you'd kind of expect them to be. Well, I wouldn't say expect them to be, but that's just what they are. Since the mean of the sample statistic targets the population statistic, in this case the statistic is proportion, this is an unbiased estimator. So, kind of a picture here from a previous book to show you what's supposed to happen with their distributions. Because what we've talked about is if it's biased or unbiased. But if you want to talk about their distributions as well, they have a really cool picture here that's kind of lost in the new book. So when they have this picture right here, what they're showing you is the, these are all your sample means, and then if you do your distribution, if you set them up kind of like I showed you with the very first example, that the distribution of the sample means actually has a normal distribution, and even the distribution of the sample proportions have a normal distribution. However, the distribution of the variance is not a normal distribution. Actually, it's a skewed right distribution, and we will get to this type of distribution in the next chapter and also the chapter after that. We'll work with all these, and that's it.